Hello guys, I hope some of you are able to write the pseudocode for Jacobi method, right? Are you able to do so?
Yes, sir.
So, would you like to tell me?
Yes, sir. Like, do I need to? Okay, I just have to dictate, or
Yeah,
I need to write
just,
this.
just
Okay. Okay. First of all, we can take the input of array, the whole array, and we
yeah,
can
yeah.
take the input of initial guesses solution. Hello.
Huh? Of what?
We
Of
can
array of matrix. This is matrix, right?
yes, 2D array matrix. We can take the input.
Okay.
Uh, then we can take the input of the initial guess, like what would be the initial guess of x1 x2,
Okay.
that thing. Then we can check for uh, whether it is a diagonal dominant or not. So we can check that, and if at any point of time we find that it is not diagonal dominant, we can end the program and return that it is not diagonal dominant, so Jacobi method is not applicable.
Okay.
And if it is diagonal dominant, then we can move forward, and we will run three loops. So the outermost one would be for the how many iterations we want. Like we will stop when we will get the stopping condition. So outermost loop for that. Then
So, what is the
the
stopping condition? What is the stopping condition?
so stopping condition means that would be given like it can be the number of iterations, or it can be the tolerance.
Okay. Yeah, true. Uh, okay. Then second loop.
Uh, Second loop would be for updating each x, like updating x1, x2, x3. So that would be for that. And the last innermost loop would be for calculating that value, like bi minus summation of aij xj,
Okay.
for that.
Hmm.
Finally, we will divide it by the pivot element aii, and then we will assign it to xi, and then we can print the solution after running till stopping condition.
So we will update in this third loop, right?
Yes.
After this third loop, first we find the sum,
Yes.
like it is moving from 1 to n, and this is also moving from 1 to n. So for this index not equal to this index, we will find the that sum bi minus ai aij. Suppose this is ith index and this is jth index. So xj, where j is not equal to I. That's what we will do, right?
Yes, sir.
We'll find some sums, and then we'll update our value with that value of x.
Yeah.
So that's what we are going to do. Very good topic. So that's how the code will look like. I hope everyone got it. Now I'll come back to this. That there, as Tucker said, there are two stopping conditions here. One is tolerance, and sec- first is iteration. The other is iteration number. So this is not a very much used stopping condition. However, it is used by some of the coders, but it is not very much uh, useful from the perspective of computer science. When you are writing the efficient codes, you do not know how after how much iterations it is going to converge, but you definitely know the correctness after which you want your value to be correct, right? I hope everyone agrees with that. Uh,
Yes,
also,
sir.
okay, so tolerance epsilon should be used as the criteria, and epsilon that too relative, that too compared with the relative error. So how the relative error is defined? So relative error will be defined by a new value minus older value divided by newer value. It is all relative. So you can use the uh, x of some previous iterations and apply your comparison on the basis of tolerance and relative error. So you have to do this. You have to run this loop till the relative error is less than the tolerance. I hope everyone got that. And how you are going to find this tolerance? So you can find this tolerance by the very formula that we use in the starting, like how after how many significant digits you want your answer correct. So that is 0.5 times 10 to the power 2 minus t. This was the value of epsilon, right? Scarborough formula. So you have to use this. So and now you will ask me what is the value of t. We should take your value, any value that you want. That completely depends on you. That the more correct the answer. Main thing is method, not what value of t you are taking. That doesn't matter. But I think it is a think it like problem in real life. You are facing, you are given some problem, and uh, you have to find some solution, right? So you should find most correct one, right? Most correct one will be found out if you apply the right concepts in right order. So this is stopping condition is very important in that sense. So this code can be easily be tweaked for Gauss Seidel method, uh, like instead of uh, like in this you are using the older values, all the older values. However, for you can, however, for the Gauss Seidel method, you can break this loop into two parts. Like so, for the ith iteration, uh, you can you can first run your inner loop from 1 to I minus 1, then from I plus 1 to n till n. The second loop I'm talking about. Uh, Hope everyone got it. So for the 1 to I minus 1, you can use the newer values that you have already updated. For the I plus 1 to n, you can use the older values. So these are the updated values and these are the older values. And by applying it successively, you will get your answer. If you have any doubt in this, then please tell. Uh, I give you 5 minutes to absorb this. After that, we'll move further. So someone has unmuted. Sorry.
Sir, can you please explain the breaking of loop again, the second loop?
Yeah. So earlier, what we are doing is that we are running this loop, this second loop from 1 to n, and this third loop also from 1 to n. But here we put the condition I not equal to j, kind of condition in Jacobi. Now, what in Gauss Seidel we have to use till 1 to I minus 1. Like we are when we are at ith position in the first loop, then we have to update xi, right? Xi we have to update. So we are of the opinion that we have already updated x1, x2 up till xi minus 1. These we have already updated, and we are yet to update xi plus 1 up till xn. Are you getting this much point? The person was asking the doubt.
Okay, sir.
So that's why I broke it up into two loops. You can, from 1 to I minus 1 and from I plus 1 to j. You can do it other way also, like putting the condition in this, but this is one of the methods that I'm telling you. You can definitely use the method of your choice. Coding is this only, that you have freedom to do whatever you want to get the same answer.
Sir,
Yeah.
sir, do we have to create two separate codes for Jacobi and Gauss Seidel, or we have to do it only in one?
You have to create separate codes for both Jacobi and Gauss-Seidel. Okay. Uh, so is it clear why we are breaking it into two loops? The person who was asking the doubt.
Yes, sir.
Okay. So I give you 5 minutes to absorb all this, uh, and then we'll move ahead to SOR, and then we'll wrap up with the session. Okay.
Sir,
Yes.
so in the second part of the question, it is asked to create a table for 25 iterations. So
Yes.
do we have to write another code for that?
Uh, what I said is that you have to check for the stopping condition, right? So
Yes.
when you will be checking the stopping condition, you will already be calculating the relative error. So there is nothing new you have to do there. Already what have been done have to be just taken into the form of a table or something like that, and you have to write it in your report.
Sir,
You
but
have
what
to.
if my code stops before 25 iterations? What if the error is lesser before 25 iterations?
If it happens, so then go by number of iterations.
Okay.
Hello, sir.
Yes.
Sir, in if just for if we go by the error checking method, then we have to check error for all the x, and when the error is low for all the x, then we have to stop or something like that. Because every x will change differently, right?
Yes. For every x, you have to check the error. Like there are two approaches to this, which you can do. That you can sum up error for the every every iteration. Like absolute, you can take the absolute sum and make it less than the tolerance. Uh, Second approach is you take mean squared of root of the sum. Are you understand how to take that mean square sum?
You said RMS value, right?
Yeah, yes, RMS value. You take the RMS value and make it less than the tolerance. So there are two ways you can do. Both will give the same answer approximately.
But sir, can't this happen that one of the x has a larger error and one of the x has a smaller, all the other x has smaller error, so the sum comes out to be low, but one x is not that correct.
The See the all the you are adding all the sum all the values, right? Uh, and that total addition is less than a particular tolerance. So when so the error in each of the x have to be less than that tolerance. Are you getting that?
Acha, okay, sir. So we will take small enough tolerance so that the sum is also small.
Yeah.
Also, sir, do we have to do pivoting in this if it doesn't comes out to be diagonally dominant? मतलब अच्छा तब तो नहीं हो पाएगी, but if first we have to do pivoting and then check, right, for diagonally dominant.
Yeah, you can directly feed your inputs that it is a diagonally dominant one. And just like Tokir said, you can write a short program to check whether it is diagonally dominant or not. There's no method like pivoting in this to make the matrix as a diagonally dominant. At least I'm not aware of such method. If you are aware, please tell.
No, no, sir, I was not saying that it will become diagonally dominant, but it may happen that the equations are written in the reverse manner. Then it may not appear to be. But just like ma'am gave an example in class where the two equations were written in a particular order, but then they were exchanged.
Mm. Can you repeat what you are saying?
Like sir, the example was like matrix was 1 2 1 then 2, in the next row was 2 then 1, so here it was 1 1 in the diagonals, but if we exchange then the diagonals will contain 2 2.
Yes. So in that case, like you have to make a program just to check whether it is diagonally dominant or not. If it is not diagonally dominant, so you have to just output that it is not a diagonally. You just print output which states that it is not a diagonally dominant matrix. Please enter a diagonally dominant matrix, like that only. And because if it is not a diagonally dominant matrix, then the solution will diverge. Iterations will happen again and again, and the solution will diverge. Hence, the diagonal dominancy is necessary. So you have to intentionally put your input in such a manner that it is a diagonally dominant one. Hope I'm
Acha.
clear.
Okay sir.
Ansari, your doubt is also clear now for diagonally dominant one. You have to just print it out that it is not a diagonally dominant.
Yes, sir.
Okay. So now we move to SOR, right? So here it is written a fact that convergence of Gauss-Seidel technique can be speeded up by a successive over relaxation method. So what does it mean? It is just a fact. Uh, so to prove this fact, there is a question given that you have to do a comparative study with taking the factor as 1.5 and compare it with Gauss-Seidel method, and you have to compare the convergence and iteration, which in which of the method the iteration happens faster, right? So what is SOR? Basically, uh, in this while updating, you have to keep the factor in mind. That here it is given as lambda, here it is given as W. So W means weighting factor, and so is the lambda means the same. Uh, so you can see here lambda times xi new plus 1 minus lambda times xi old. So this is the weighted average of uh, the new and old values. The new values is, and this is Gauss-Seidel. This this is just a Gauss-Seidel method and not applicable to Jacobi. Or you may apply to Jacobi. I'm not no significant results were happened. That's why it is not taken into consideration in the Jacobi method. So Gauss Seidel is much more better than Jacobi, so it is used to improve the accuracy of Gauss Seidel, right? So you know the section formula, right? So if the value is uh, between 0 and 1, then the resulting value will lie between xi old and xi new. The formula is, suppose there is some line segment or something, and we have divided into lambda is to 1, or like lambda is to, yeah, lambda is to 1 minus lambda. The whole line segment is 1. So how these two values are weighed, so that this distance is known. So what we do is we take the coordinate of this and take x1, x2. So what it ensures it is that the uh, resulting point resulting point is lying between this x1 and x2. So when the resulting point will lie between x new and x old, so obviously the results are going to be slower. The iterations are going to be slower because there is a reason to it. Suppose uh, the lambda is 0, then that is we are updating xi new with old value only. So this becomes a Jacobi method, right? Are you all agreeing me on that?
Yes, sir.
So this becomes a Jacobi method, and when lambda is 1, this becomes a Gauss-Seidel method. So between Jacobi and Gauss-Seidel method, everything will be slower than Gauss-Seidel method and will be faster than Jacobi method. That much should be clear. And now, if we take lambda to be between 1 and 2, which is called over relaxation, that is, we are weighting the new values more than the older values. So, uh, this is called over relaxation. So, the point will not lie between these two uh, 2 points, but lie beneath that. So, extra weight, as written here, extra weight is present on the value. So just a small modification when you are like updating the value, right? So you will update some value here for Gauss Seidel, and you have to just write xi, the same xi to be lambda times xi plus 1 minus lambda times xi minus 1. You have to write the of the previous iteration, right? Of the previous iteration, you will store in some variable or so, so that you are able to easily access it. Are you all getting it? What I mean to say, and what you should get in the end, that this method is uh, converging faster than what Gauss Seidel used to do. So that's all what is there in SOR and so on. If anyone have any doubt, you can ask. Otherwise, the session is over for today.
Hello.
Yes, I.
Is there in this question 2, can you just once clarify this root of sigma error I square? which error are they talking about here? Is it the absolute or the relative one? Question 2.
Yeah.
Is it this error?
This error. So as I said that you are going to find the relative error in every x, right? And you have to take RMS value of it. This is basically the RMS value.
Uh, but sir, they haven't divided by n.
Yeah.
RMS is like root
So
of mean
yeah,
of squares, right?
yes. So if you do that or this or that, that doesn't make any difference because it will be just divided by n. And nothing else will be there.
So in the question, we have to calculate exactly this, which is written, right?
Yeah, yeah, yeah. You don't have to divide by n in the question. But while checking that stopping condition, you have to divide it by n. Like, hello.
Uh, uh, we have to divide by n there.
Yeah, you have to divide it by the n there because there you have to check for the root mean squared error for all the uh, numbers. Because if you see if there are three variables, then there is no problem. If there are n variables, then then the number is so high that error might not converge to that value. So it is of the order n. So to cancel that order of n due to summation, we have to use that divide by n so that the iteration and convergence is assured in that sense.
But sir, if we calculate RMS, then to that rule won't apply, na? Ki every error will be less than, because some errors will be greater than the central tendency.
Okay.
Like if we take just the sum or summation, then to we can say ki every error will be less than it. But if we take RMS, then to there will be some errors, right? That will be greater than, and it will
Right,
get averaged out.
right, right. You're saying right. So then don't divide it by n, right? So don't divide it by n.
Sure, okay, sir.
Anyone have any other doubt? If not, then let's call it a day. Uh, you may join the doubt session. All of you have to join the doubt session.
Okay, sir.
You have to join the lecture class link for that. It will start from 6. So you may leave from here and join there. I'm stopping the recording here.